Hello everybody, this is Satya Malik, and today I'm going to show you how to use OpenCV AI Kit with depth, OAK-D, or its little sister OAK-D Lite, or its other variants like OAK-D PoE to estimate the depth of a scene. This video is part of a series where I'm going through various features of OpenCV AI Kit, and in the previous video, you had already seen how to get the two images from the left and the right cameras. In this video, we are going to show you the depth map, how to estimate the depth map, and I will also show you some interesting things about stereo depth estimation, the general principles of stereo depth estimation. So let's go over the demo first, and then I will go over the code. So here we are looking at the depth map that is output by this camera when we set up the pipeline correctly. And on the right-hand side, we are looking at the left and right views of the camera. Let me just show you the two views and how I have merged them together. So here you can see that there are two views, the left and the right views. And there is a different view. If you press T, which is for toggle the views, we can merge them together onto the same view. As I had mentioned in the previous video, if you look at this, the disparity, the two views, the two cameras, the left and the right cameras, when they look at a person, the parts of the person which are closer, they look very separate. You can see that my face, you can almost see two copies of my face on this video. On the other hand, if you actually look at something that is far away, you will notice that they are pretty much aligned. So, which gives you an idea, how depth camera works, because it is looking at stuff from two different viewpoints. The things that are close, they look far apart. So that concept called disparity, where the same point, if you focus on, let's say, the tip of my ear or the top of my head, you will notice that the same point in the two cameras, it is separated by a certain number of pixels. And that is called disparity. And what you're looking at on the left-hand side is the disparity map. The disparity map is directly related to the depth map. It is basically the depth is directly proportional or inversely proportional to the disparity. The larger the disparity, the closer the thing is to the camera. Now you can see the output has been color mapped. What does that mean? It means that it is actually grayscale. It gives us a single value, but to make the visualization pretty, we have mapped it into a color map, and this particular color map is called jet. This jet color map basically goes from cool, blue, to red. Anything that is cool is a small value. So we are actually plotting the disparity here. So you can see that the disparity between pixels, they are very close when things are far away, and the disparity is large when things are close by. And you can look at my hand. As I bring the hand closer, it gets hotter and hotter, which means that it is closer to the camera. Now, the second thing I want you to note is look around the around this area. You can see that you can almost see a shadow around my hands where the depth is incorrect. It is actually set to something. It is set to 0. Why is that? The answer to that is both the cameras. If you look at this area, both the cameras are not able to see this portion of my finger, and that is why the depth is incorrect. For the depth to be right, both the cameras need to see that point, and so it can triangulate. So there are two reasons why the depth could be incorrect. First of all, it cannot see. Both the cameras do not see the same point, in which case it doesn't know where the depth is. It becomes monocular vision. And that, we can estimate, we can know, oh, we actually cannot see it from both the cameras. And we are doing that in this case, and we are actually setting that depth to something like 0, so we can easily identify that those pixels are incorrect. So that's one piece. The second reason why a depth estimate can be wrong is when you cannot match 2 points. So the idea is that the points can be uniquely matched. One pixel in one image has a counterpart in the second image, and you're able to match them perfectly. And if you are unable to do that for whatever reason, in that case, the depth estimates are wrong. And usually what happens if the surface is smooth, it is completely, let's say you're looking at a white wall from two different viewpoints, then every pixel in the white wall is similar. So it's very difficult to match exact points. Even though both the cameras are looking at the wall, they may not be able to say that, oh, this pixel, this point on the wall matches to this pixel in the left camera and this pixel on the right camera. So, those are the reasons why depth estimate could be wrong. Another reason is, let me show you something. So if you look at my hand right now, it is red, which means that, okay, it is closer to the camera than my face. Now let me push it slightly more. Ooh, you can see that the depth is completely wrong. You see, up until now, the depth is good in this range, but when I push it beyond a certain point, the depth is incorrect. Why is that? The reason is that when we search for corresponding pixels, like I said before, the two cameras need to look at the same 3D point, and they should be able to say that, oh, this 3D point in the left camera is at this location, and on the right camera, it is at a different location. And the disparity between the two locations would give us an estimate of depth. However, to make this processing fast, we do not search the entire space. We do not search the entire space. We search for this disparity in a range. And when you are too close, when the hand is too close to the camera, we'll need to search a lot. We'll need to search a lot for pixels to match. And for things, for making things faster, we don't search in that range. Now, there is a way in Depth AI API to make that search space larger. It makes the depth estimation slower, but it is certainly possible. But the reason we are unable to get accurate depth, there is a minimum distance from the camera. If you violate that, in that case, the depth would be inaccurate because we are not searching for corresponding points in these two, in the two views. Now, the other thing I wanted to show in this demo is the concept of rectification. Now, let me switch on to the other view. All right. So in this view, you will notice that the two images, as you could see that they are, when you in the overlapping view, you could see that there is a disparity when things are closer, and the disparity is smaller when things are far away. But let's say we want to search for corresponding points, right? I'll click on this point, which is the corner of this door. You will notice that when I clicked on this is the red line is the scan line. And if you notice that this pixel, the corresponding pixel is right here, and the corresponding pixel in this case actually is on the same scan line. It is on the same row of the image. And this is true about every, corresponding point. Let's say I click on the bottom of my ear. The bottom of my ear in the other image also lies on this line. Fascinating. This is accomplished using something called image rectification. In image rectification, you transform the images of a stereo view so that all corresponding points lie on a scan line. So you pick any point on here. The corresponding point in the second image lies on the same scan line. So why is it important? Imagine that you had to do this stereo matching, right? So you take a patch from this left image, and you want to find the corresponding patch in the right image. If you had to search the entire image, that's a big search space. Let's say we have 1,000 by 1,000 image. That search space is big, right? It is 1 million locations. And at 1 million locations, if you try to do that comparison, it's a lot. So we don't need to. Fortunately, we don't need to do that. smarter people than us have figured out that you can actually rectify the two images. And this rectification depends on the location of the two cameras only, the orientation of the two cameras with respect to each other. And once you do this rectification, the search space becomes linear, which means that for any point in the left image, you just need to look at all the pixels along this line to figure out the match. The match has to lie on that line when you rectify the images. And these two views are called rectified views. But like I had mentioned just a few minutes back, we actually don't even search for all the pixels in this line, along this line. We take the corresponding pixel here. Let's say this pixel right here is somewhere here. And then we search in a neighborhood of that pixel to find the match. Because we know that we have already set the minimum depth of the that we are going to estimate. Once you have set the minimum depth, we know how much disparity we need to search for. So we need to search for only a small area along this line, not this entire line. If you search for the entire line, things can become noisy. Not only that, it will also become slower because you're searching along all the pixels. So here you can see that what kind of optimization was done. From 1 million locations, if you had a 1,000 by 1,000 image, you had 1 million locations to choose from. We were reduced to 1,000 locations because now you need to search only along a row. But even that we do not do. We would search for, let's say, 200 locations around that corresponding pixel and find the best matching location. So that speeds up first we got it down to 1,000 times, and then we got it down by another 5 or 6 times so that stereo matching can be done in real time. So that was the concept of stereo vision. I just want to summarize a few things that we learned here. First of all, we learned that we need 2 views to do stereo vision, where we estimate the depth. Second, we learned that the disparity between the 2 views provides an estimate of the depth. When things are close, then corresponding points are far away in the picture, in the left and right views. And that disparity is inversely proportional to the depth. If the disparity is large, we are closer to the camera. If the disparity is small, we are far away from the camera. And that helps us estimate the depth. The fourth thing is that there's a lot of optimization done based on the geometry of the camera. You can get something called rectified views. And in these rectified images, the left and the right corresponding points, they lie on the same scan line. So the search space is greatly reduced. Final thing that we learned is occlusions. If the cameras cannot see the same point, then the depth estimate there would not be good. If the matching is incorrect, let's say you're on a white wall, if the matching is incorrect, then the cameras will not be able to match the 2 views correctly, and the depth would be wrong. So even shiny surfaces is another example where you can have very wrong depth because here we assume, when we do the matching, we assume that the appearance of the object, the appearance of the point doesn't change from one view to the next. But if you look at shiny surfaces, the same point can have very different appearance when you move your eyes, because it's glossy. The highlight will move on the surface, and the appearance of that particular point will change dramatically. And that is why shiny surfaces do not do a good job in stereo vision. The final thing is that there is a minimum distance below which the disparity doesn't work, because in our algorithm, we search for disparity from a certain range to a certain range only. So the depth estimate becomes incorrect if you're not a certain distance from the camera. With that, let's see how to implement this on OpenCV AI Kit with the depth, OAK-D, OAK-D Lite, or OAK-D PoE. Before I show you the code, let me actually show you the pipeline. In the previous video, we had seen how OAK-D, OAK-D Lite, and OAK-D PoE all use the Depth AI API. And the API is based on the concept of pipeline. A pipeline consists of nodes. Nodes have inputs and outputs. For example, the mono camera is a node with which outputs the mono image, and these nodes can be connected to form the pipeline. So let's see what the pipeline looks like for stereo vision. As we can see, the left camera gets its input through this X-link. If you remember, X-link is used as a communication medium. This node is used for communicating between the device and the host. So this input, this is no different from the previous slides that you had seen. So X-link is used to control the left camera, also to control the right camera. The output of the left and the right cameras, they now go into this new node called stereo depth. If you can go to Luxonis, you'll notice that this node has the left and the right as input. These are images, and then it has several outputs. The outputs that we are interested in for this demo are rectified left, and this is nothing but the left rectified image, and rectified right, which is nothing but the right rectified image. And we are interested in disparity, this one. But you can also get the depth directly in, I cannot remember the units, maybe it is millimeters or centimeters, but you can get the depth map out. But as a proxy, we are using the disparity map because it's easier to display. All right, so that stereo depth, as you can see, that our outputs are rectified left, rectified right, and this disparity, right? And these are basically X-link out links. I have not mentioned it to remove clutter, but these three are X-link out nodes. All right, so this is what the pipeline looks like. Now let's check out what the code looks like. So the code will look very familiar to people who have gone over the last video. Just like before, we have a function to get the frame. All it does, it gets the last frame from the output queue and gets the frame. We convert the frame to an OpenCV format. Similarly, this code is exactly from the last video. We get the mono camera, we set the few parameters of the mono camera, set the sensor resolution to 640 by 400, and then we indicate whether we are talking about the left camera or the right camera. Now, this one is new code. Here, we are actually passing in the pipeline and the left and the right mono cameras. So we first get the stereo pair, which is basically stereo equals pipeline.create stereo depth. So this stereo depth node is being created. Just to tell you briefly what set left right check does, it actually checks for occlusion. It figures out which pixels are likely to be occluded, and it sets the value of those pixels to 0 or something that we can identify. So if you don't do that, you will see a very noisy output where there is occlusion. And sometimes it may be okay when you want performance, because there is a small performance hit when you do this check. And if you don't care about that performance hit, then you should set it. Otherwise, for many applications, you may not even need to set it because you are just looking for very gross information about the object. Next, we need to set the output of the mono left camera and the mono right camera to the input left and input right of the stereo pair. And that is it. Others are pretty easy. Let's go over the code. This is a mouse callback function. What we are doing is when we click on the screen, we are recording the X and Y location of those clicks. So let's go over the main code. This is these are variables for the X and Y coordinate of our click. As before, we first define the pipeline using depth.ai.pipeline. And we have imported depth.ai using this command, depth.ai as DAI. Okay. So next, this code is exactly the same as what we had shown last time. We say mono left equals get mono camera. So you get the mono camera. For the left camera, you set it to true. For the right camera, you say that it is the right camera by setting is left to false. And then we combine them into this stereo pair. Basically, we are taking the output of the mono camera, the left mono camera and the right mono camera, and putting them as input to the stereo camera using this line of code. And we have already seen the details of this function. And now you can see that we are setting out the X-link out for disparity, rectified left, rectified right. We also had other options. You can go into the documentation and see that we could have gotten the depth estimate directly, but we are interested in just displaying what the depth looks like. So disparity is used as a proxy for depth in this case. Yeah, so these lines of code, we are just setting up the output X-link out. And then, as you remember from the last video, we will also need to create a queue for all of these. As you can see here, we are basically getting the disparity and linking it to X out disp, which is the X out link for disparity. Similarly, we are doing the same thing for rectified left and rectified right. These lines of code basically query the output queue and get the frames back. Now, this disparity, basically we want to map this disparity between 0 and 255 because that's for visualization, that's where the range should be. And so we are going to multiply the disparity by this number. 255 here is because of the fact that we have 255 grayscale values to show. So we are setting it in that range. We are multiplying this amount. We then set the stereo pair. There are two windows that we are going to show. For the stereo pair, where we are showing both the views of the camera, from the two cameras, we are setting the mouse callback function also, so that when I click, I'm able to get the X and Y location and draw that line. This side-by-side view is set to false initially because we are showing the view where both of them are together. And when it is true, then we have those side-by-side views. The code here, it's pretty simple. Now we get the disparity. We do a get frame. We have already seen the code for get frame. And we send in the disparity queue and get the last frame. So this disparity now contains the disparity information. But for display purposes, we need to multiply it with this disparity multiplier and then convert this thing to uint8 format. Uint8 is nothing but 0 to 255. That's the format we use for display. Otherwise, it won't look right. Not only that, we also apply a color map jet onto the disparity so that we can easily see this as a color image instead of a grayscale image. You can also see it as a grayscale image. It doesn't look as good as this colored version. And then we get the frame for the left and the right rectified views. And here we are simply stacking them side by side, or if the side by side is set to false, in that case, we are just putting them one on top of each other with, half the values are coming from one frame, half is coming from the other frame. Next, we convert this image to color. And the reason we are converting it to color is because we want to draw color lines on top of it. And here we are drawing a line based on the location of the mouse X and mouse Y. As you had seen before, this mouse callback ensures that we know where the mouse location is. And you can see here that if the left button is pushed down, in that case, we are recording the X and Y location. And we are storing this X and Y location of the mouse down in mouse X and mouse Y. And those are used right here to draw the line. So from the current location, we are drawing the line all the way out to the end of the image. Sorry for this hard coding, but I'll just leave it there. We are drawing a red line here with thickness 2. Similarly, we are also drawing a circle at that location. This is just for display purposes. This circle is greenish looking or cyan looking circle. And then we just display the two images. If we hit Q, then the program terminates. If we press T, in that case, the toggle, the views, the side-by-side view and the one on top view, they are toggled. I hope this tutorial was useful and you got a good idea about stereo vision and depth AI. I hope this is simple for you, after going through this lines of code. If you look at the lines of code, they are like 100 lines, only half of them are comments. So not a lot of code you need to write to get this thing going. If you do not already have OAK-D, OAK-D Lite, or OAK-D PoE, I highly recommend to get one of these so that you can get your hands dirty with stereo vision. But not only stereo vision, this is spatial AI. And in the follow-up videos, I'll show you how to combine artificial intelligence with depth estimation to do some fun, interesting projects. Thank you.